Okay. Okay, so last time we did finish the greedy algorithms chapter. I mean, we didn't finish the chapter, but there were two more things that, if you are interested, you can go and have a look at on your own. So today we'll start with another technique of algorithm design, which is going to be divide and conquer. Okay, but okay, so let's see what that is. What's the date today? Okay. So what is this? I mean, you must have seen some examples of divide and conquer in your data structures and algorithms course, but then we'll be looking at more and more things. So, but what is the basic principle, right? So the basic principle of divide and conquer is that we break the input into parts. Solve the parts, and then finally combine the solutions to get a solution for the original instance. Okay. So that is the main idea, that we get it, and then we'll be looking at example. For example, there is one such thing which is merge sort, right? But there is one thing which is like slightly different here, or it will be more involved here, which is going to be the running time analysis. And we'll arrive at the running times by solving recurrences. Why? Because we are looking at a bigger problem, and then we are going to smaller problems and solving it recursively, right? So how much time to solve? The recurrence will depend on these things. Smaller problems, and then how much time to combine. And there is one like minor point, that the algorithms that we are going to, so we saw that for some of the problems, the brute force algorithms were in like earlier chapter, like we saw this spanning tree problem. There could be too many spanning trees. There could be an exponential number of spanning trees. Similarly, there can be exponential number of paths among which we are finding the shortest paths, and so on. So going through the brute force in earlier thing, so brute force might be still polynomial in this case. In case of divide and conquer. So, but we will use divide and conquer to get better running times, better polynomial running times only. I mean, this is just a fine point. I mean, this is not very important, but this might come to somebody's head that, okay, I mean, we can anyway get a polynomial time algorithm very easily by doing, some sort of brute force. So why are we going for divide and conquer? Because generally we get better running times. Okay, so one example, as I said, you must have seen in data structures course is merge sort, and I'm not going to describe, but what does the algorithm do? The array which is not sorted divides it into two parts of size n over 2, recursively solves them, okay, and then combines them. after it gets the solution of both both of them, it combines them, and the combining gets done in order and time. So how does the combining gets done in order and time? Anyone? So you're given two sorted arrays. You want to form one array.
We compare only the first elements.
Yeah, so we keep a pointer in both the arrays, and we keep comparing, and we keep moving so we have one array, we have two smaller arrays, we keep a pointer here, we keep a pointer here, and then we compare these two. Whatever is smaller, we put here and increase that pointer further. Then we compare these two, and so on. I mean, you must have seen it. Okay. So this will take linear time, because here also you'll make one traversal, here also you'll make one traversal each. So good. So this is actually one principle that is sort of used in divide and conquer, which is divide the input into equal parts, or two equal parts, let's say. And solve each of them, and then take linear time to merge the solutions. Okay. So what is the recurrence that we'll get for this? And yeah, so of course there should be some base case. So suppose the base case is when you are left with just two elements, then you don't actually recurse. You just compare them and return the sorted list. Where sorted list, right? Or array, whatever. So I mean, when there are just two elements, then you don't need to recurse. Good. So what is going to be the recurrence for this? Suppose so any problem that follows this, then what is going to be the recurrence for this? So let's say Tn is the time that it takes to solve the problem of size n.
2 times
we can write 2 times Tn by 2 plus order of
that's order of merging.
Yeah. So let's say Cn, or let's say order n. Okay, fine. But I mean, this order n, we can replace it by that it is less than or equal to some Cn. So let's say that Tn is equal to Cn. Suppose linear time it takes. Suppose it takes Cn time to solve the this. And let's say that T of 2 is something, is equal, also C, is less than or equal to C. Okay. So yeah, I mean, you can replace this C. If T of 2 is higher, then you can replace this C by that, and otherwise you can replace the otherwise it's fine. The same C will work for 2. That is not, this C is a constant, so will not create much problem. So don't get confused by why are these two C's the same. Okay, good. So this is a very typical recurrence. I mean, and I mean, not just merge sort, but any algorithm that will follow this paradigm, that divide the input into two equal parts, and then just basically solve the parts recursively and then combine them in linear time. This is going to be the same recurrence, right? Now, I mean, some other way of this can be another generalization can be that Tn is equal to some Tk, where k is some other. Sorry, I mean some 2 or something depend. It depends on TK. Instead of n over 2, right? Where k is some function, some linear function, or k is alpha n for some n, some alpha less than 1, something like that. And so anyway, so this is the main recurrence that, like, we get if the problem sizes are going to be equal, and if there are two problems there, right? So there is one, like, again, finer point that maybe n over 2 is not an integer. So in which case it should have actually been maybe, ceiling or something. But then, like, we are going to ignore this because asymptotically it will not make much of a difference. Okay. Good. So now, so this is the recurrence that we got, that okay, fine. This is whatever Tn is equal to Tn over 2 plus Cn, and T of 2 is less than or equal to C, let's say. Yeah. Now, this is the, like, recurrence we got, but this does not give us an explicit bound. Okay. So now there are some, like, different ways of how to get these explicit bounds for Tn, and we'll go through them one by one. And then, like, if time permits, we'll look at one more example. So we'll go through it for this particular recurrence. We'll solve it for we'll solve this particular recurrence using the techniques. And if time permits, look at more examples. Okay. So good. Like, two basic ways are, like, expansion, or let's say unrolling the recurrence, and substitution. So let's see what that means. So first one, let's say unrolling. Yeah, let's call it unrolling because the book calls it unrolling. So what does it mean? That here it means that, okay, we look at the recurrence and we see what happens. Okay, so the first level is size of the problem is n. Second level it's n over 2, and we have two subproblems. Third level we have four subproblems of size n over 4, right? And so on. So how much time do we spend at first level? In the like, in the tree we spend Cn time, right? Because what does the recurrence say? That at that level we spend Cn time to combine the solutions. So we spend Cn time at the first level. How much time we spend at this level? 2 times Cn over 2 is equal to Cn. Here we spend 4 times Cn over 4 is Cn, right? So we get some pattern. What is the pattern here? Okay, let's look at the pattern, like, more formally. So at level J, so suppose this is level 0, this is level 1, this is level 2, and so on. At level J, how many subproblems are going to be there?
Two to the power j.
2 to the power J subproblems. And what is going to be their size?
N by 2 to the power j each.
N by 2 to the power J, right? Because it gets half the every time, we go down the recursion tree, the size of the problem and the number of problems double at every level, right? each level? Is again so 2 to the j many subproblems, and for solving each of them, it's just a linear c times n over 2 to the j is equal to cn, right? So we have cn time at each level. So that turns out to be very like neat. That here also it is cn, at every level it's cn. Very nice. Now we just sum over all the levels. How many levels are going to be there?
Log n.
Log n levels, right? So and so summing, what do we get over all the levels? Total time is okay. Why did I write the same thing? Yes. Total time is equal to cn log 2 base n, which is equal to order and log. So this is how you. This is one way of solving this particular recurrence. That you unroll it and then look at how much time it takes on each level, and then you just you just sum it up for every level to get the thing that is needed, the time that you require. Okay. So I mean, if you want to now write it as a lemma that any function that is or that satisfies the recurrence is bounded by order and log. So this you can say. Okay, now look at the second method, which is substitution. So here we make a guess. So suppose we believe somehow we already have some idea that what it should be. Okay, so suppose we know that suppose Tn is going to be Cn log n. We already know. And now we want to show this by induction. So I mean Tn is less than or equal to, not equal to, of course. Did I say above? Yeah, there it's fine. So suppose we want to upper bound Tn by Cn log base 2 n, and we want to show this by induction. So first, let's say we want to show T2 is equal to, then it comes out to be C2C, which is less than or equal to 2. Yeah. Sorry. But we know that T of 2 actually is, okay, this is not the way to write it. Let's say, so for n is equal to 2, we get that Cn log 2 base n is equal to 2C, which is less than greater than or equal to T of 2. So for base case, this is fine, that T of 2 is less than or equal to this function. I mean, this is strictly greater than for positive C, but it's fine. Anyway, we just need less than or equal to or greater than or equal to. That is not the problematic thing. All right. So the base case is done. Now suppose for all m less than n, we have this inequality, right? That T of m is less than or equal to, what do we have? C of m log 2 base m. Right? So suppose we have that, and now we want to show that. So in induction step, we want to show that for t of n, right? We want to show the same inequality for t of n. So let's take t of n. We know that it's equal to C or 2Tn over 2 plus Cn. So this is what we get from the recurrence. And then now we substitute. We substitute the value of T of n over 2 from the recurrence itself. And since P of n over 2 is strictly less than n, n over 2 is strictly less than n, we can apply the induction hypothesis, which is going to be 2 times, now T of n over 2 is going to be C n over 2. So here it will be less than or equal to log 2 base n over 2 plus C, right? So this gets cancelled. So you get Cn log 2 base n over 2 plus Cn, right? Then you get Cn log n minus 1 because this is base 2 and like log base 2, 2 is 1 and plus Cn, and then you get Cn log n minus Cn plus Cn. Cancel. So you get Cn log n, which is what you wanted. So you have shown that Tn is less than or equal to Cn log n for all n greater than or equal to 2. Right? So which means that Tn is order n log n. So I mean, this is very straightforward, but still, is there any question? I mean, it might not be straightforward also for some. Is there any question about this? That what are the methods and how do they differ, and what do we do in each of the methods? Any question? No. All right. So if not, then there is another method which is because this substitution method, like how do we know that this is going to be like the same C that is there in the recurrence, for example? Like how do we come up with this guess? If somehow we reach the correct guess, then it's fine. But like who tells us? So if we don't, then there is a way that is called partial substitution. So here we make a rough guess. So what does it mean by like making a rough guess? That we don't like guess exactly. We sort of guess partially. So what do I mean by that? For example, that suppose we have an idea that Tn is going to be order of n log n, but we don't know what the constant is going to be, what the C is going to be. So what we'll put Tn is less than or equal to Kn log n, let's say log b base n. We don't know which base here it will be, but again that is not generally an issue because that will just get multiplied by a constant thing, and that can get absorbed in the k. But I mean, let's go through it just for the sake of clarity. That suppose we make the guess that Tn is less than equal to Kn log b base n. So n is equal to 2 t of n over 2 plus cn, and now we want to replace this. So this is less than or equal to, because of induction hypothesis, 2k n over 2 log n over 2 log b base n over 2, right? Plus cn. Okay. So now again, like here this b is if we take b is equal to 2, then again we get this nice thing that we got above, that it becomes log 2 base n minus 1. So let's take b equal to 2, and then we can fix like k also later. So then this becomes 2k n over 2. Okay, so let's write this kn, and then you get log of 2 base n minus 1 plus cn, right? And what do we want to show? We want to show that this whole quantity is less than or equal to kn log 2 base n or b base n, right? And b is equal to 2. So this is what we want to show, right? So, okay. Maybe I should have written one more step. So let's say this is kn log 2 base n minus kn plus cn, right? And I want to show this, like, to be this whole thing to be, as I said, less than or equal to this. So this is, you can say that this is plus c minus k n. So what does that mean? That what do we want this quantity to be now? What should this quantity be?
It should be 0.
It can be like, we want less than or equal to, right? Say. Say again, someone.
It should be less than 0.
So this should be less than 0, right? Or at most 0. So what does that mean? That c minus k should be at most 0. So k is greater than or equal to c. So any value of k greater than or equal to c, if we put here, it will suffice. So for any value of k greater than or equal to c, what do we get? That p of n is less than or equal to k n log 2 base n for all k greater than or equal to c, right? So basically, if we replace c there, then it is correct. So Pn is less than or equal to Cn log 2 base n. And again, we get Tn is equal to order. Okay. So this is a method where we don't make an exact guess, and we arrive at it by putting the values appropriately so that our induction hypothesis goes through. Our induction step goes through. Of course, you also need to check the base case here, that t of 2 should be less than or equal to whatever this k n log 2 base n. We need to show that, and just take k to be large enough. Okay, and then you can use the same k. If this k works, fine. Otherwise, you can use a bigger k and substitute there also, that bigger k. That is change it. So these
So
are the
why,
three methods here.
excuse me, so why is
Say-
k important here? K is a random constant, right? Why did you say k should be greater than or equal to c or something? I mean, in the last step itself, we could have said that t will be of order n log n, right?
The last point I did not hear.
I was
Say
saying
again.
in the last step itself, we could have said T is order n log n.
Last
Above,
step where? Here.
no sir, above what you wrote, K is greater than or equal to C. No,
Here.
yeah, yeah, huh.
I mean, we need some K to do that. What is our induction hypothesis? Or what do we want to show? That Tn is less than or equal to Kn log n for some fixed K. This K does not or should not depend on n. So you need to fix this constant. Okay?
Okay.
So here we don't know what this K is going to be. This K is a variable to me. We need to fix some value so that we can actually say that Tn is less than or equal to Kn log n for some constant K. And that is why I fix this constant in the end, and I say that okay, this constant is actually the same constant C. We can fix it to that or anything larger than C also, and it. But we need to explicitly find a constant that satisfies this for this to be order n. Otherwise, if suppose this whatever, then you can't put it in, right?
Yes. And sir, in that equation, Tn is 2 Tn by 2 plus Cn. That C is also fixed independent of n.
Yes, that C is fixed independent of n because we are taking some linear time here for merging the operation. So whatever order n, that order n is going to be, again, by definition of order n, there exists a C such that this order n, whatever this function is less than or equal to some Cn. So this is that C which is independent of n, definitely. All right, so let's look at some more recurrences. Like having So let's look at the same recurrence, but I mean similar recurrence. But now suppose we don't have just two subproblems, exactly two subproblems, but we have some q subproblems of size n over 2, right? So suppose Tn is less than or equal to some q of t of n over 2, and plus again, but we take like linear time for merging, right? And again we have this t of 2 is less than or equal to c. So now suppose this q is there. This q was 2 earlier. So in the case above, this q was 2. But now what if q is 1 or q is greater than 2, right? And these two cases are actually different. So let's look at them differently. So let's first look at the case when q is greater than 2. Okay. So now let's apply both the methods. So let's look at the unrolling method first. So we have this one problem of size n. Now we have q problems. So let's say if q is equal to 3, my diagram is going to be for that. So this is n over 2, n over 2, n over 2. Then we have 3 here, 3 here, 3 here, right? And so on. So, okay, so let's just write in unrolling. So levels and patterns and level. So what is the pattern? How many subproblems at jth level?
Q to the power j.
2 to the j. Sorry. And what are some problems? What is the size?
N by 2 to the power j.
n over 2 to the power j, right? Good. So what is now total work at each level? Work at level is now each subproblem has n over 2 to the j size. There are q over 2 to the q to the j problems times c n over 2 to the j time. Right? So this is the work done at each level. So what is the total time? Is total time spent at all the levels, right? And so let's say, so this is again, so 0th level to, actually the number of levels is going to be log 2 base j, log 2 base n levels. But the last level is going to be log 2 base n minus 1 because you stop at 2, you don't go till 1, right? Suppose, because the base case is 2. So now what do we get? Tn is equal to summation of q is equal to 0 to log 2 base n minus 1. So these are the n levels and q over 2 to the j. Okay, so let's, slightly simplify it, times cn. Right. So just stop me if, like, you don't understand anything in the steps, in any of the steps. Okay, please stop. So now we take the cn out.
Excuse me, sir.
Yeah.
The summation should be over j, right?
Yeah. Q is fixed. Thank you. Good. So now we take the cn out. J is equal to 0 to log 2 base n minus 1. Q is, of course, I mean, it's whatever greater than 2, which is a constant, and that is fixed. And now you have Q over 2 to the J. Right? And now this is a geometric sum. And Q over 2 is greater than 1. So we apply the geometric sum formula for greater than 1. The first term is going to be 1. So A, whatever R to the n minus 1, R to the power n. So, okay, let me just apply it. Sn is equal to A times R to the n minus 1 divided by R minus 1, right? This is right. So then apply this here. So you get Tn is less than or equal to Cn times R to the power log 2 base n minus 1 divided by R minus 1. Right? Just applying this formula over this sum. And then what do we get? So we can ignore this minus 1 because we just want less than or equal to. So strictly less than we can say here. Cn R to the log 2 base n minus 1 divided by R minus 1. And let's just, like, slightly rearrange it so that we can get the constant terms out. N R to the power of 2 base. Right. Now we want this, like, this n r to the power log 2 base, and, like, we have to we want it in nicer form of some formula of n, and for that we use this this equality that a to the log b is equal to b to the power. Okay, so this is a very neat inequality if a b are greater than 1. So what do we get then? Then we get this is equal to c over r minus 1 n times n to the log two base q over 2, or let's say, so here the r was q over 2. Right? If I started with this r, what was this r? This r was q over 2. So I apply r is equal to q over 2, which is the ratio of the terms. And then I write this formula. So now I get, when I replace this, so instead of r to the log 2 base n, I get n to the log 2 base r, which is c r minus 1 n times n to the log 2 base q over 2 n to the log 2 base q minus 1. So basically what you get is c over r minus 1 n to the log 2 base q. This 1 gets cancelled with this line, right? And what is this? What is this c over r minus 1? Again, r is just a constant depending on q, right? So, I mean, whatever, c over q something. And q is a fixed constant. Q over 2 minus 1. Let's say. And to the log 2 base q. So, basically, what you get, this is order n to the log n. Sorry. Yeah, n to the log 2 base q. Okay, so this is, and what is this? This log 2 base q is greater than basically 1, but still a constant. Right? Depending on q. So, for example, if q is equal to 3, then we get this number is order n to the 1 point something, 1.59. And when q is equal to 4, this is the value of log 2 base q, log 2 base 3 actually. If q is equal to 4, then we get n square because log 2 base 2 is, log 2 base 4 is 2, and so on. So these are of course polynomials which grow faster than n log n, and like, yeah, in fact they grow faster than any n to the log, any power of log, because they are polynomials. I mean super linear polynomials. Okay, good. So any question about this particular, that how did we sum it up, and any problem with this? So let's just look at the substitution method here, and in substitution method, because this is, suppose we don't know this, this is a very tricky exponent to guess, because we might not know that what is the exponent going to be. Like this is such a strange looking, that log 2 base q. How will we guess that? So let's say that we cannot guess exactly. So let's look at partial substitution. The same recurrence with the partial substitution method. So suppose we guess, so we don't know what is it going to be. Suppose we guess is, or guess is Tn is less than or equal to some Kn to the D. We guess that it is some polynomial, but we don't know what power it is going to be and what is going to be the constant, right? So now, again, let's write the recurrence and substitute. So Tn is less than or equal to Q Tn over 2 plus Cn is equal to Qt, okay, less than or equal to Qt k n over 2 to the d plus cn, right? So now we want to show this. There is no t here. Yeah. So what do we want to show? We want to show that this whole quantity is less than or equal to k. Okay, let's take out the constants. Q over 2 to the d, k to the d, k n to the d, right? Plus c. Okay. Now we want to show that all of this is less than or equal to k n to the d, for us to show the that this works because by induction. So that means this quantity, let's say, should be equal to 1, right? Suppose we want to put it equal to 1, so we put because we want to fix the value, right, of k and d. That is the point. So let's say q over 2 to the d we want to be 1, so we put d is equal to log 2 base q, right? So you see that this exponent comes like very naturally. That if we put d is equal to log 2 base q, then this becomes 1 and this becomes. But we want to get rid of this cn also. So that is not happening. So what do we get? If we put that here, we get k n to the d for this particular d plus cn. But this is not what we want. We want this to be less than or equal to k n to the d. And that does not seem very easy to get from here. That how do we go from here and just remove this cn like without doing anything? So that is why we can. There is another way to do it, which is strengthening the induction hypothesis, right? So change the guess to be something stronger. So now we want our guess to involve a negative term, some negative term that will basically that can offset this cn term that we are getting that we don't want, so that they cancel out. Okay. So now we will take this guess to be, let's say, Tn is less than or equal to Q, I guess, K n to the D minus some ln. Okay, let's say. And now suppose we have fixed this D, that we have gotten close with this D. So we take this D to be log base 2 Q. And suppose this is our new guess. So let's again do substitution. So Tn is less than or equal to Q Tn over 2 plus Cn, and now we substitute. So this is equal to or less than or equal to, because we are substituting, K Q K Q K K n over 2 to the D minus L n over 2 plus Cn, right? So which is equal to, yeah, I mean, if you solve this, I'm going to write the simplified term. So Q over 2 to the D, again, K n to the D minus Q L n over 2 plus Cn. Okay, I'm not simplifying yet. So this is 1 because we have D is equal to log 2 base Q. So it's equal to K n to the D minus Q L n over 2 plus Cn. And then this whole thing to be less than or equal to k n to the d. That means we want Cn minus q n over 2 to be less than or equal to 0. That means nc minus q ln over 2, ql over 2 to be less than or equal to 0. And so basically we want C minus QL over 2 to the less than equal to 0. Right? So we can choose the L because L was our guess. This L is our guess. So we choose L such that this is satisfied. Basically, we'll get like, L greater than or equal to some 2C over Q minus 2.
Sir, should it not be in the
Yeah.
top equation Cn minus QLn by 2 less than equal to minus Cn? Because Tn also has a minus Cn term in it.
Say again, sorry.
This Cn minus QLn by 2 less than equal to
C.
minus Cn, should it not be, right? Because Cn is the Cn term is also in Tn.
You're right, you're right. Yeah. Good. Thank you. Because we have another Cn which is coming from here. So, yeah. Good. So, yeah, but then you get whatever 2C here, and then you get 2C here. All right. You're right. Okay, so but you can choose L such that it satisfies that equation and so on.
So why minus Cn?
Say again.
Why? Should be minus ln, right? We want to prove this is less than equal to k and raised to d minus ln.
Yes. Again. Good. You guys are following. I'm glad. Yeah. So less than equal to. So here you don't get 2C. You get less than equal to minus 1. But again, the point is that you can still figure it out. So the n gets cancelled, and then you can find the value of L. Okay. So you want this QL over 2 minus C to be less than equal to minus L. Okay. Yep. So yeah, the calculation will change slightly. I would have made a mistake, but you can choose L such that this is satisfied, and then we are good. And this L should turn out to be positive. I mean, so C minus QL over 2 should be less than or equal to minus L. C less than or equal to minus L QL over 2. And Q over 2 is, of course, greater than 1. So this is fine. So C less than or equal to L Q over 2 1. So L is equal to C over Q over 2 minus 1, which is positive. Yeah. Okay. I mean, I might have made some mistake, but like, again, you also need to do the base case. Just choose the K large enough such that it satisfies the K is equal to N is equal to 2 case. Okay, so now we solved this recurrence. Now let's just quickly, like in 2 minutes, when Q is equal to 1, that is the case we had not seen. So when Q is equal to 1, the case is like, at what does it mean? That there is just one sub problem. So n over 2, n over 4, and so on. And we take Cn time at every level. So here we take Cn over 2, here we take Cn over 4. So the recurrence is going to be very simple. Tn is equal to summation j is equal to 0 to log n, whatever. Cn over 2 to the j. On that level, and it turns out to be, this will turn out to be less than or equal to 2Cn. So this is just, I just did it the, unrolling case, and this is easy. So the thing is that for q is equal to 1, you get order n. For q is equal to 2, you get order n log n. And for q is equal to or q greater than 2, you get order n to the log 2 base q, right? So these cases are different, that the running time, of course, increases when you increase the queue because the number of subproblems increase, and that is why you are getting more and more. And this is almost like, so this is just linear multiplied with n, and this is something bigger, polynomial itself. So this is the difference between, and there is another recurrence which is there in the book, which we'll see. So I'll just mention that particular recurrence, which is Pn is equal to 2n over 2, 2tn over 2 plus order n square instead of n. So we take quadratic time. So what does that mean? That, okay, at first level I have one subproblem, second level I have 2, third level I have 4, and so on. But the time that I'm taking is n square, not n, right? So again, the number of instances is the same, n over 2 to the j, right? The size. The number of instances is 2 to the j, and size is n over 2 to the j. But the time that is going to take is n over 2 to the j c times, let's say, n square of this, right? And times 2 to the j, something like that, at each level, right? So you get c n over 2 to the j is the time, c n to n square over 2 to the j is the time taken at each level. So now you sum that up, j is equal to 0 to log 2 base n minus 1, because the number of levels is going to be exactly the same. And you sum what? Cn square divided by 2 to the j. And this is going to be again a geometric sum. And surprisingly, it comes out to be, if you do the calculation, I mean, this is order n square only. So the thing is that if you are spending more time, c n square here, if you spend cn, then somehow, a factor gets added of log n. But if it is cn square, then it does not get added. And why it does not get added? Because if you have cn square, then n over 2 square decreases much faster as compared to n square, as n over 2 decreases as compared to n. Because now it's going to be n over 4. The next time you will get n over 8. And like, the decrease is going to be exponential, right? I mean, the decrease is going to be geometric, let's say, not exponential. And there the decrease was linear. Like an arithmetic progression, the decrease was happening. At every level, it was decreasing by a constant factor. Here, it's going to be in a geometric progression. And that is why, since you lose so much time, that is why it turns out to be order n square only and not order n square log n. Of course, it is order n square log n also, but you get a tighter count. Okay. So, I mean, these are the things you can play around with this and see if there is any other recurrences also you can, see, make up and, try to solve. And from next lecture, now we'll be looking at algorithms. So this was just the general idea, just to give you that how do we solve these recurrences, these are the methods, and how do we go about it. Any questions about this? Any quick questions? We are out of time, but any quick questions about this? If not, then we meet on Thursday, and thank you all for coming.